你也开着了吗？
有，然后到时候我再把影片剪一剪。
没事。
因为今天刚好2个。对。
就只有最后去，然后就讲5集，然后就散会了。香港没有一起来看。大家耗费资源可大。卢布跟苏大都有去，对不对？那他们讲什么？好吧，你可能因为你比较早去，你可能会遇到老师会去。真的？好，真的吗？没事，我只是说，如果你遇到老师，是很有今天的事情，如果他记得进去了，原定我是我早期是跟他说我跟你去的，但是呢，就他可能说怎么你在这里要修成，就说不要上课。我因为我没有特别跟他说今天做了什么有人去，不知道他有什么兴趣，但我比较喜欢学一些。辛苦。你有这个权吗？就是那个王大哥的女儿，他付，你们就各付各的。就是看完他就马上下车就走。没关系，那你没吃400块。你有400块，不过多的就你赚的，对不对？一个分别是固定多少钱？400块。没关系，我会核销参与，按记得到底票我买它。那我们上课。 start this chapter 6, and I'm sorry, today I have another meeting at 6 o'clock, so we will finish the class at 6 o'clock. Okay, so let's get started with the chapter 6, structure analysis. Okay, the first thing introduced is the simple trusses. For a bridge, the load on the deck is first transmitted to stringers, then the flow beam, and finally to the joint of the two supporting side trusses, like roof truss. The bridge truss loading is also coplanar. When the bridge or roof trusses extend over large distance, a rocker or roller, like this, is commonly used for supporting one end, like this joint point A. This type of support allowed freedom for expansion or construction of the member due to a change in temperature or application of loads. Okay, so next we will explain the assumptions for design. All loadings are applied at the joint. Okay, so the weight of the member is neglected. The members are jointed together by smooth beam. Okay, so like this part and this part. Then we assume the connections provided the center line of the joining members are concurrent. So every trusses we can use one line combined together. Connect on the one point. Okay, this is also. Then we call concurrent. Okay, this is the class case about the Uplift I-35 West Bridge. You can see so many trusses were connected to the gusset blade using the rivets. Okay, like this. And the failure often originates from the connection at the gusset plate. So like this part. For example, corrosion can reduce its connecting capacity. Okay, so each truss member will act as a two-force member. So like this part and this part always is two-force member. The two-force member means the same direction and okay, the force direction on the same line. Okay, so we can call this is the and this two force is same, so we can call this is a two-force member. And this we have the two assumptions. First, the first one is if the force tends to elongate the member, it is the tensile force. So like this part, we have this two force, then let the truss have a tensile force. The second one is if the force tends to shorten the member, it is a compressive force. So like this figure. Okay. And the triangular truss is rigid, like this figure. We use a triangular truss, and this is 1 unit. Okay, 1 unit. If you use the we have the one triangular truss, and we have the other triangular truss. We call this is the simple truss. So Simple truss is a truss can be constructed by extending the base triangular truss. Therefore, we can combine many triangular trusses into the simple truss. Okay, so let's begin by introducing the method of joints. For truss, we need to know the force in each members. So we can use the method of joint to solve the problem. And the entire truss and each of its joints are in equilibrium. The mean is force equilibrium equation can be used to obtain the member forces. And the force system acting at each joint is coplanar and concurrent. So we can use these two equations to solve the problem. Summation fx equals to 0 and summation fy equals to 0. Okay. So like this triangular truss, at the point B, we apply a force, and there are also two reactions from the trusses. Okay, like these two trusses. So we can draw the free body diagram about the point B. Okay, so we have this force, and if we have this force, the reaction, okay, FBC. I think the direction from this to this, because summation f x is equal to 0, so the direction from this to this, and the reaction FBA, because we have this force, so we have the force from bottom to top, so we have the FBA direction like this. Okay, so this free body diagram on the point B, but the truss will give this reaction. So FBC from this direction to point B, the mean is the truss. Okay, truss BC get the compression. Okay, get the compression. And the truss BA get the tension, get the tensile force. Okay, so like we can draw like free body diagram again. This is the point B, and we have this force, and this reaction force, and this also reaction force. C, A. And for truss object, like this, will reaction force at here. Okay. So reaction force at this direction. So this is a pressure, and this is tension. And if you combine these two, we call this is the internal force. This is the external force, but this is the internal force. So when you combine these two parts, well, we don't show this part. Okay. About the free body diagram. Okay, and let's see. Okay. At least one known force and at most two unknown force. Okay, so we can use using the summation fx equals to 0 and summation fy equals to 0, and two members to determine the current sense of the unknown member force. First one, the current correct sense of the direction of unknown force can be determined by inspection. The second is always assume the unknown member forces acting on the joint free body diagram to be in tension. So when we draw the free body diagram, we can according to these two assume. But this part, we know this force, so we can very easy to draw the free body diagram this direction and this direction. If you don't know, just put the tension. It's okay like this part. Okay. Then when you calculate, you will get the negative value. Okay. You will get the negative value. And in free body diagram, we show the force value. If the force value is positive, we call the tension. If the force value is negative, then we call the compression. Okay. Okay, so we can see this example. Determine the force in each member of the truss shown in this figure, and indicate whether the members are in tension or compression. Okay, so we can draw this free body diagram first, then check every truss, maybe tension or compression. Okay, so like this power. So first one, we draw the object, and we have the three connect points, and we have the two supports. One is the hinge, and one is the roller. And we put the force at here, 100 Newton. Okay. Okay, so before this chart, we just draw the free body diagram about the reaction and the force. So we also do this. So we have this and this, because this is a hinge. We use other part. And point C also like this. If you use the method of the joint, we need to check each internal force. So just draw like this. So we know this part we have this direction force, and this part also have this direction force, and this part this and this. So this truss is the two force member. So the force go like this, and okay. So and point A will get this internal force, and this also. Okay, so like this. Okay, then we need to calculate every force. If the force is positive, I think this is a compression, and this also maybe I just try to calculate this. If the negative mean is the tension, okay, just try to calculate. So we can use the point joint B, do the summation Fx equals to 0 and the summation Fy equals to 0. So if at joint B, you can see like the force may be like this. Okay, if the direction is different, just the value have the negative and the positive. Okay, so we can use the summation Fx equal to 0, do this first. So like this equation, then we can get the FBC answer. Okay. And we can also do the summation Fy equal to 0, then we can get the FBA answer like this. Okay, so the direction is different.
calculate at joint C. At the joint C, we also do the summation fx equal to 0. So when we do the summation x equal to 0, we can very easy use this diagram to calculate the FCA equal to 500 Newton tension. And we also can use the summation Fy equals to 0, then we can easily to calculate the Cy equal to 500 Newton. And about the point A, joint A, we also do summation Fx equal to 0 and summation Fy equal to 0 again. So we can very easy to get the reaction force here. And if you want to know this part, I think you use the previous method is also okay, because we can use this force, then calculate this reaction force and this relation force and this. Then we can very easy to get this value, and get these two value again. Okay. So use the previous method, also we can get the answer. But now we just learn how to use the method of the joint. Okay, next example. Determine the force acting in our members of a truss as shown in this figure. Okay, so we just check every truss force. Okay, so we need to draw the free body diagram first. Okay, so in previous method, we just use these two force. Okay, we have the one force at here, and we have the two support. This support is hinge, and this support is roller. So we have the two in hinge part we have the two reactions, and in roller part we have the one perpendicular reaction. And when you set the moment point at here, you just do the summation Ma equal to 0. So this force let moment point A acting according to the right hand rule. The moment is positive, and then use the force times the moment on, and we can get the moment. But this moment is equal to 0, so we can use this force times this moment on. Then, according to the right hand rule, this force let the point A get the negative moment. So these two moments summary together is equal to 0. So we can very easy to find the reaction on the point C. And we also can do the summation Fx and summation Fy. Then we can get the reaction at point A. So when we do the summation Fx, just this force and this force. So the point A, Fax is equal to -3 kilonewton, and direction like this. And when we do the summation Fy equal to 0, just this force and this force. Okay, so then we can draw, because we need to use the method of joint, then determine every truss is the internal force. So we can do the joint C first. Okay, so joint C here, and we have the one reaction force and the two truss force. So the free body diagram like this. Then we can do the summation Fx equal to 0 and the summation Fy equal to 0. Then we just get use these two equations, we can get the answer. And we also can rotate the coordinate, okay, the coordinate, the axis. So we can use the same concept get the answer, because this axis just rotate like this, and we also can use the equation very easy to calculate the answer. And about the joint C, we also do the draw the free body diagram, and we have the one force answer, CD, FCD, so at here. And we do the summation Fx equal to 0 and the summation Fy equal to 0. Then we can calculate this FDA first, because x direction. So we can very easy to calculate the FDA first. Then use these two answer to resolve and calculate the FDB. So like this part. So answer like this. Okay. And we also can use the same concept. Use the point. I think this is the point A. Then we know the 1 and 2 and 3 force, just unknown 1 force. So I think it's very easy to calculate the answer at here. Okay, next example, determine the force in each member of the truss as shown like this figure, indicate whether the member are in tension or compression. Okay, so just do again. We have the one truss at here, and we have the two support. One is the hinge, and one is the roller. So at the hinge support, we have the two direction reactions, and the roller support, we have the perpendicular reaction. And we have the two force put at the point B and the point D. Okay, so the free body diagram may be like this. Then we can calculate the reactions first. So we can do the summation Fx equal to 0. So we can see in this free body diagram the Cy will equal to this. So the Cy equal to the 600 Newton. Then we can put the moment point at the point C. Then calculate the moment. Okay, this force let this point get the positive moment. Okay, so we use the moment times the moment arm, and this force let point C get the negative moment according to the right hand roll, okay, times the moment arm. And we also can use this force let the point C get the positive moment. And summary, these three moments together is equal to 0. Then you can calculate the Ay equal to 600 Newton. Then we can also do the summation Fy equal to 0. So this force, okay, negative this force minus this force, then plus this force is equal to 0. So we can get the Cy answer is equal to 200 Newton. Okay, when we calculate the truss internal force, then we draw the free body diagram about the point A and point B, C, D. So first we do the joint A. Okay, so we have the one known force and the two unknown force at here. So we can do the summation Fy equal to 0. So use this force, and this force times the 4 divided by 5. Then summary this 2 is equal to 0. So the FAB is equal to 715 Newton. Then this, because of this direction, so the truss will get this direction force. So the force is compression. And we do the summation Fx equals to 0. So we have this force x divided into the x direction force, then plus this force is equal to 0. So FDA is equal to 450 Newton. And because the force direction like this, so the truss maybe get the internal force from this to this, or from this to this. So the force is the tension. We also can draw a free body diagram about the joint D. Then we know these two force, and we need to calculate these two force. So we also can do the summation Fx equals to 0. Then we can calculate the FEB. So like this part. Okay. And when we have because we assume the direction like this, the force direction like this. If you get the force value is negative, mean is the direction from this to this. So let the truss get the reaction like this to this. So the truss, the force is tension. Is a tension. The tension force. And we also can do the summation Fy equals to 0. So just use this force and this force. Okay. The answer like this. Then I think the joint C also, we have 1, 2, 3 force known. We just unknown one force here. So it's very easy, just this force equal to this force. And then we also can use the summation Fy equals to 0 to check. Okay, just check. Okay, so the method of the joint, the free body diagram like this part. Okay, so you can see, okay, point A, the free body diagram like this, the point B like this, point C, point D. And we have the internal force at here, and here, and here. Okay. And if you want to draw a total free body diagram, like this, just like this. Okay. If you use the method of joint, just draw like this. Okay. Let's move on to introduce the zero force member. Truss analysis using a member or a joint is greatly simplified if we can first identify a load members, which is called no loading. Okay, like this truss, you can see every truss have the force, so we don't have the zero force member. And okay, maybe like this part. Okay, this part, when you calculate the internal force, Fa and Fe and Ed and Dc, no internal force. So these two parts we call the zero force member. But what need to do this zero force member? Okay. When using the method of joint for calculation, the zero force member are used to increase the stable of the truss during the constructions and to provide added support if the loading is a change. Okay, so like this figure, we also can use the this is enough. but just in static part, in static situation, if the part maybe get the other force, okay, maybe like earthquake or something, then this part not static. We need to use like this zero force member, and this zero force member to support this truss very stable. Okay, so this just the concept, and we need to learn how to check every truss. Okay, which truss is the zero force member. But I think next class we can continue to introduce this part, because I have other meeting at this time. Okay, so today class started here. Okay, thank you. But this part, I think the being, how to say,